How to calculate entropy in complex engineering processes. Have you ever wondered how engineers calculate entropy in complex processes? Understanding this concept is essential in thermodynamics and mechanical engineering. Let's break it down step by step. First, we need to grasp the basic definition of entropy. Entropy is a measure of disorder or randomness in a system. It plays a significant role in analyzing energy transformations and efficiency. The change in entropy, often represented as the symbol delta S, can be calculated using the formula delta S equals Q divided by T for reversible processes. Here, Q stands for heat transfer, and T represents temperature. In simpler thermodynamic processes, like the isothermal expansion of an ideal gas, we can use the formula delta S equals nR times the natural logarithm of V divided by V naught. In this equation, N is the number of moles of gas, R is the gas constant, and V naught are the final and initial volumes respectively. This formula is handy when the temperature remains constant, but volume or pressure changes. Now, when we move to more complex scenarios, things get a bit trickier. For processes involving multiple phases or chemical reactions, we need to apply entropy balances. This involves using the entropy balance equation for open systems. We account for entropy flow due to heat transfer, work, and mass flow across system boundaries. This includes terms like entropy transfer by heat, entropy generation due to irreversibilities, and entropy carried by mass entering or leaving the system. Next, computational methods come into play. Engineers often use techniques like normal mode analysis and free volume theory. These methods help simulate molecular interactions and structural changes to estimate entropy changes in chemical and phase change processes. Another useful approach is the incremental method. For example, when heating water, we can calculate the change in entropy incrementally. By dividing the temperature range into small steps and calculating the change in enthalpy for each step, we can sum these increments to find the total entropy change. In real processes, we also need to consider entropy production. This occurs due to irreversibility. To calculate this, detailed process modeling is necessary. Identifying sources of inefficiency, such as friction and mixing, is key. In practice, engineers use thermodynamic property tables, software tools, and process simulators to calculate entropy changes accurately. This information is vital for optimizing process design and improving energy efficiency. So, calculating entropy in complex engineering processes involves combining fundamental thermodynamic relations with advanced computational methods. By understanding these principles, engineers can tackle various challenges in their field effectively.